Hello everyone, this is lecture 18. In the last lecture, we talked about the series solution of Legendre polynomials. In this lecture, we are going to talk about generating function, orthogonality, Rodrigue's formula, and recurrence relation for the Legendre polynomials. The generating function for the Legendre polynomial Pnx. Okay, so the Legendre polynomials are the coefficients of z power n in the expansion of 1 minus 2xz plus z square whole power minus half. Okay, that means this function 1 minus 2xz plus z square power minus half is the generating function for the Legendre polynomials Pnx. So that means that if we expand this function into infinite series, then Pnx are the coefficient of z power n. Okay, so we can, if you put n 0 1 2 so on, so you will find that p naught x plus p1 x z plus p2 x z square plus so on. This is the infinite series, and Legendre polynomials, they are coefficients of powers of z. Okay. So we are going to prove this. So we know that 1 minus t raised to power minus half, its expansion is this. Okay, where and this can be rewritten easily into this form, where for the second term, if we multiply with 2 and divide with 2, we can write it as 2 factorial by 2 square. For the third term, if we multiply and divide with 2 and 4, so 2 and 4 multiplied and divide, so our numerator will become 4 factorial, and in the denominator we can write it as 2 factorial square and 2 power 4. Similarly, in the third term, if we multiply with 2 4 6 and divide with 2 4 6, then numerator will be 6 factorial and denominator will be 3 factorial square 2 power 6. Okay, so in general, for t power n, if we multiply with the even terms 2 4 6 so on and divide with same, we can rewrite into this form. Okay, so this expansion is known, and in this, if I substitute now t as this 2xz minus z square, then I can find the expansion of this left hand side. Okay, so the expansion of the left hand side using this formula is this 2xz minus z square can be written as z into 2x minus z. So if I put t as z into 2x minus z here, then I will have this infinite series. Okay, here I have put simply t as z into 2x minus z everywhere in this series. So we have to calculate the different powers of z here. So in fact, if we try and calculate the coefficient of or terms of z power n from this, okay, so z power n coefficient, we have to prove it is Pnx. So if you see this term, then already there is a z power n outside, so only constant term from here will make this whole term as z power n. Okay, and all the terms after this, the next term will be z power n plus 1 into 2x minus z power n plus 1. So z power n plus 1 is already outside, so there will be no term of z power n. Similarly, for any term after this particular term, and the z power n term will not be there. There will be powers higher than z power n. So z power n term will come from here. In one previous term to this, the power will be z power n minus 1 into 2x minus z power n minus 1. So z power n minus 1 is outside, so the z term from here will make it z power n. Okay, similarly, if we look at this term, then z power n minus r is outside and 2x minus z power n minus r, so it will make the one term from z power n will come from here when we take z power r term from the expansion of this 2x minus z power n minus r. So z power r into this will make it z power n. Okay, so the coefficient or the term of z power n will be there. So this term and previous terms, but up to some limit. Okay, because this will not give z power n if in n is say 6 8 8 10 12 so on. So if we look carefully here, then if I put r0 here in this term, So it will be this term. Okay, r1 will be one previous term, r2 will be further previous term. So this will give z power n when r is n by 2. When r is n by 2, it will be z power n by 2, and this power will be n by 2. So z power n by 2 can come from here and z power n by 2 here, so that will make z power n. Okay, if n is even. Okay, if n is odd, then it will be n minus 1 by 2. So let us okay now write the terms of z power n uh, from this particular uh, term. Okay, so the term of z power n in this, or that is this term, will be when z power n minus r is already there. So if z power r term comes out from here. Okay, so we know that we can expand this into like binomial. So z power r will come when we have n minus r cr z power r and 2x power n minus 2r. Okay, so this will be the term. This coefficient is already there, 2n minus 2r factorial, n minus r factorial squared, 2 power 2n minus 2r, this term, and z power n minus r is already there. If we expand this, then only this term of from here will be making this product as z power n. It is n minus r cr, so that we have minus z power r and 2x power n minus r, so n minus 2r. So it is minus 1 power r, which is here. This term is already there. Z power r and z power n minus r will make it z power n, x power n minus r, which is this term, and we know n minus r cr means n minus r factorial in the numerator, which will cancel out with this one power, so it will be only 1 power of n minus r factorial, and in the denominator r factorial, so that r factorial, and this minus this means n minus 2r factorial, so there is a n minus 2r factorial, and then there is a 2 power n minus r, which will cancel out with this to give 2 power n. Okay, so 2 power n. So basically the term of z power n in this expansion is this. Okay, and with r value 0 it will be for this term, with r value 1 it will be one previous term, and so on. Okay, so in general the terms of z power n in this whole expansion will be when this r varies from 0 1 2 3 so on up to uh, say capital N, where capital N is n by 2 or n minus 1 by 2, depending upon this n is even or odd. So we can write that if we collect all the terms of z power n in the expansion, we see that the terms in z power n are that term we said, with r value varying from 0 1 2 so on up to some capital N, where this capital N uh, is n by 2 or n minus 1 by 2, depending upon n is even or n is odd. Okay, and because this summation is already known by the name pnx, so we can write this as pnx z power n. So we immediately see that p and x are the coefficient of z power n in the expansion that we use. So that proves our formula for the generating function, that is this function is the generating function for the Legendre polynomials. Okay. So the second result that we are going to prove today is the Rodrigue's formula, and the formula says that the Legendre polynomial Pnx can be written as this: 1 by 2 power n factorial into nth derivative of x square minus 1 power n. Okay, this is known as the Rodrigue's formula. So now we are going to prove this. So to start with, let this x square minus 1 power n be equal to some function v. Okay, so we assume that v is equal to this x square minus 1 power n, and we differentiate this one time with respect to x, and so dv by dx is n x square minus power n minus 1 into derivative of inner, which is 2x, and dv by dx we denote it by v1. Okay, so this subscript means derivative. Okay, and this because x square minus 1 power n is v, so we can substitute and we can rewrite this. So we take this x square minus 1 to other side and just rearrange the terms to write that 1 minus x square v1 plus 2nxv is 0. Now we know that Leibniz rule for derivative, that if you have product of two functions, then its nth derivative can be calculated as this. Okay. So basically we want to calculate the n plus 1 derivatives of this. So differentiating this n plus 1 times. Okay. So and using this Leibniz rule, it is simple. Okay. So differentiating n plus 1 times by Leibniz rule. So we have 1 minus x square as f function and v1 as g function. So it is will be n plus 1 c0, which is 1, into this function into its n plus 1 derivative, so v n plus 2, because already one derivative is there. Then n plus 1 c1, and n plus 1 c1 value is n plus 1, into this first derivative of this, which is minus 2x, and nth derivative of this, which is vn plus 1. Then plus n plus 1 c2, and n plus 1 c2 means if you expand, then n plus 2 over 2 factorial into n plus 2 minus sorry, n plus 1 minus 2. So that will give this n into n plus 1 by 2. Second derivative of this, which is minus 2, and n minus first derivative of this, which is vn. Okay. So what we have is this term, its first derivative, its second derivative. So next derivative of minus 2 will be 0. So all the other derivatives, further derivatives, will be 0. So only these three terms from here. Similarly, if we differentiate this part n plus 1 times, so 2n is a constant. So n plus 1 c0, which is 1, this x into n plus 1 derivative of this, so x vn plus 1, plus n plus 1 c1, which is n plus 1, the first derivative of x. Okay, so one derivative of this, which is 1, and one previous one integral of this, which is vn. So and further other terms will be 0. The next derivative of one constant is 0, so all other terms are 0. So we can just cancel out this to rearrange this equation. Okay, so if we rearrange, then we find that this is 1 minus x square vn plus 2 minus 2x vn plus 1 plus n into n plus 1 vn equal to 0, which is a Legendre differential equation. Okay, so this function vn satisfies the Legendre differential equation. Okay, so that means vn is a solution of this Legendre equation. But we know that the Legendre function Pnx is a solution of this equation. Okay, so because Pnx is solution of this equation and Vn is also a solution of this equation, so Vn must be a constant multiple of Pnx. That is, we can write Vn is equal to C times Pnx. Okay, and from here, because V is known and Vn means nth derivative of V, and V is this. Okay, so C times Pnx can be written as nth derivative of this function x square minus 1 power n. Okay, so C times Pnx is nth derivative of x square minus 1n. Okay, so it is almost, we are here. Okay, C times Pnx is nth derivative of this. If we prove that C is this 2n 2 power n factorial, then we can divide with C and we have this result. Okay, so that's what we are going to prove. So C times Pnx is Vn, and Vn V can be written as this. Okay, so just rewrite this. C times Pnx is Vn, and V n means nth derivative of V. So nth derivative of what V is. Okay, so this x square minus 1 power n, so x square minus 1 can be written as x plus 1 into x minus 1. Okay, so we'll just rewrite this, and again we can apply that derivative of f function into g function. So again Leibniz rule we can apply here, and the derivative of these two. Okay, so nc0, first function, nth derivative of second function, plus nc1. Okay, so first derivative of this function f, and n minus first derivative of g, plus on ncn, the second function, and nth derivative of first function. Okay, so nth derivative of this x minus 1 power n is nothing but n factorial. So this n factorial. Okay, and n minus first derivative of this will give some term of x minus 1, some number times x minus 1. Similarly, this x minus 1 power n will remain here. So all these terms will contain at least 1 power of x minus 1. So we can simply write that this is nc0 is 1, so it is x plus 1 n into n factorial. So this first term is this x plus 1 power n factorial, and rest of the terms, for them we can write the terms containing powers of x minus 1. Okay, So we just want to calculate this constant. So if I put x is equal to 1 in this equation, then all these terms will be 0. 1 factorial is 1 and it will be 2 power n, and it will be pn1, and we know that pn1 is 1. Okay, so when pn1 is 1, so if we substitute x is equal to 1 on this both sides, then we can calculate that c times pn1, and pn1 is 1, so c must be equal to 2 power n factorial, and because these terms are 0. Okay, so once we have this constant, we can put it back here, and c times pnx is equal to this derivative term, so pnx must be 1 by c of this, and c is this. Okay, so that immediately gives us pnx as 1 by c, c is known, times the nth derivative. So that's the Rodrigue formula, so we have proved it, right? So third term thing that we are going to do today is the orthogonality of Legendre polynomials, and it says that the uh, integral -1 to 1 of pmx pnx dx is 0 if m is not equal to n, or it is 2 over 2n plus 1 if m equals n. Okay, so we'll prove this orthogonality part first, that this Legendre polynomial, when integrated from -1 to 1, their product is 0 if m is not equal to n. So let us take this case where when m is not equal to n. Okay, so when m is not equal to n, then pmx is a Legendre polynomial which is a solution of Legendre equation, and pnx is also a Legendre polynomial which is a solution of Legendre equation. So both pmx and pnx, they are solutions of Legendre equation, so they will satisfy the Legendre equation. Okay, so say 1 pnx satisfy Legendre equation, 2 pmx satisfy Legendre equation. Now what we do is we multiply this first equation with the pmx and this second equation with pnx, and we subtract these two. Okay, so multiply 1 with pmx and 2 by pnx and subtract. Okay, so 1 minus x square is common, so pmx times this minus pnx times this. Similarly, minus 2x is common in these two, so pmx times this and minus pnx times this, and from here pmx pnx, and here pnx pmx, so pmx pnx are common, so we have n into n plus 1 minus m into m plus 1. Okay, so we can easily rewrite this 1 minus x square common into this, minus 2x common into difference, and plus pmx pnx common into difference. Okay, so the first term, this, and the second term can be combined into a single derivative term, so it is derivative of 1 minus x square of pmx derivative pnx minus pnx derivative pmx. Okay, so if you see that first function into derivative of this will be this, and this second function into derivative of 1 minus x square, which is minus 2x, so minus 2x times this. Okay, so these two can be combined into a single term, and this term inside the bracket, it is n square minus m square and n minus m, so n minus m can be taken outside into n plus m plus 1. Okay, so this can be rewritten. So from here we can calculate this pnx into pmx as minus of this. Okay, so this term was brought from left hand side to right hand side. Now if we integrate both sides with respect to x from -1 to 1, okay, then these are constants. Integral is -1 to 1 pnx pmx dx, and on this side it will be integral of derivative, so that is function itself, limits -1 to 1. So if we put upper limit 1, so this 1 minus x square will be 0. Okay, so this product is 0, and if we put x value -1, lower value, so again this 1 minus x square is 0. So this on both limits this value is 0. Okay, so it is equal to 0, and because m is not equal to n, so this term is non-zero, this term is non-zero, so we can divide with this. Okay, so we immediately get the result that -1 to 1 pnx pmx dx must be equal to 0 for m not equal to n. Okay, so this is the first part of this orthogonality condition. The second result is for the case when m equals n. Okay, so when m equals n, then pmx and pnx are same function, so instead of two equations we have only one equation, so this process cannot be used. So in that case we use the generating function. Okay, and we know that this is the generating function and it is equal to this series. Okay, so we square both sides of this equation. Okay, so squaring both sides, so what we have is this side will become power minus 1, and on this side this whole square. Okay, so this summation is like a plus b plus c so on whole square, and we know, like, for example, a plus b whole square is a square plus b square plus 2ab. Okay, so it gives a square of individual terms and plus 2 times product of a and b. Okay, so if we have summation this whole square, it will give square of individual terms. Okay, so summation of square of individual, so it's like a square plus b square type terms, and plus summation of 2 times AB type terms. Okay, so 2AB type terms. So 2 times Pnx, Pkx, where n cannot be equal to k. Okay, so n cannot be equal to k, and both n and k varies from the starting to end, so 0 to infinity, and z power n into z power k means z power n plus k. Okay, so this summation square is summation individual term square plus summation 2 times Pnx, Pkx, z power n plus k. Now we just integrate this both sides from minus 1 to 1, and when we integrate this from minus 1 to 1, and because n is not equal to k, then from case 1 this must be 0. So this second summation will become 0 when we integrate from minus 1 to 1, and this is a 1 by function, so we can solve this left hand side, and then we have a solution that we require. Okay, so just integrating this from minus 1 to 1, so left hand side integral plus integral of first term and integral of this, and because this is 0 because of case a. Okay, by case a this so this whole summation is 0. So from here we can calculate this summation must be equal to integral of this. Okay, and this is integration with x, so which is linear in denominator, so its integral is log function. Okay, so we can simply integrate, substitute the upper limit minus lower limit. Okay, so that we can do, so it that will be, this will be 1 minus the whole square on upper limit, so 2 cancels, and on the lower limit it will come 1 plus the whole square, so these 2 will cancel with that. Okay, and then we know the expansion of log function, so we can expand this into infinite series and also this into infinite series. Okay, and then we can combine these two terms to write it as 2 times this, and this can be written in a summation. So on both sides we have summation, and so we can compare the coefficient of z power 2n. So on this side it is integral minus 1 to 1 pn square x dx, and on this side it is 2 over 2n plus 1. So that gives our result for the orthogonality condition. When m equals n, the pmx become pn square x dx. Okay, so this proves our orthogonality result. Okay, so this result is also important, say in like if we are given any function and we have to write that function in terms of Legendre polynomials, then the coefficients of Legendre polynomials we can calculate using this orthogonality relation. Okay, just try some numericals on this, you will find it good. One last thing that we are going to do today is the recurrence relations for the Legendre polynomials, and just like Bessel's there are many, so I'm just going to give you two examples here. Okay, the first recurrence relation is 2n plus 1 times x pnx is equal to n plus 1 pn plus 1x plus n into pn minus 1x. Okay, and second is n pnx is x pn dash x minus pn minus 1 dash x, where dash denotes derivative with respect to x. Okay, so let us try and prove the first one using the generating function. Okay, so we know this is the equation for the generating function of Legendre, and uh, there is in the first equation there is no derivative of Legendre polynomial, so we will not differentiate this equation with x, because differentiating with x means derivatives of x. In the second there are derivatives of x. Okay, and second thing is that the coefficient contains n. Okay, and that will happen only when we differentiate with z. Okay, so if we differentiate with z, it will give n z n minus 1. Okay, so coefficient n will come when there is a derivative with z. Okay, so in second there are derivative with z because n is in the coefficient, also there is a derivative with x, but in the first there is only derivative with z, there is no derivative with x. Okay, so let us differentiate, see how to solve this. Let us differentiate this equation with respect to z. Okay, so once we differentiate, so it is minus half whole raised to power minus 3 by 2 into derivative of this with z inner part, so it is minus 2x plus 2z. So minus half can cancel out, it will become x minus z, and this power minus half can be substituted back from here. Okay, so we can just rewrite x minus z. The power minus half is substituted back, and one power will go to other side, which is written here. Okay, and then if we compare different powers of z on both z power n on both sides. Okay, so x time this will give x p n x, and z time this will become z power n plus 1. So to get z power n we have to reduce this to pn minus 1. Okay, so just equating coefficient of z power n on both sides. Okay, so this first will be x p n x. From here it is z power n plus 1, so for z power n it is pn minus 1x. 1 times this, so it is z power n minus 1. So to z power n we have to reduce, increase 1, so pn plus 1 into n plus 1. Okay, so n plus 1 pn plus 1 minus 2x z power n, so minus 2x n pnx, minus 2x n pnx, and z square will make it z power n plus 1, so we have to reduce 1n. Okay, so n minus 1 pn minus 1x. Okay, and then we just rearrange them. Okay, combine the terms of pnx and pn minus 1x, we will see that you get this result, first result. Okay, now to prove the second result, again we start with the generating function, and in this case we require coefficient as n, so we need to differentiate with z. Okay, so let us differentiate with z one time. Okay, so we already did this in previous example, so left hand side becomes this and right hand side is this. Okay, also we need derivative of Legendre polynomial, so let us again differentiate first equation with respect to x. Okay, so if we differentiate this with respect to x, then this will be pn dash x, and on this side it is minus half this power minus 3 by 2 into the derivative with x of this, so which is minus 2x. So minus half into minus 2x will become minus 2z will become z. Okay, now we can eliminate this bracket term from here, and to do that we multiply this equation with x minus z on both sides. Okay, so we multiply on both sides with x minus z, and then this x minus z times this term power minus 3 by 2, this can be substituted from here as summation. Okay, so we just substitute this on the left hand side, okay, using 2, and then we equate this equation for z power n. Okay, so equating coefficient of z power n on both sides, so here it is z power n, so npn x, x time this, so x time pn dash x, so z power n, and it is z power n plus 1. Okay, this z multiplied with this, so to find z power n coefficient it will be pn minus 1 dash x. Okay, so this is the our second result. Okay, so this is how you can prove different recurrence relation for Legendre polynomials. So we close this topic here. Okay, so from the next lecture we'll talk about Laplace transforms. Have a very good day.